Elasticity. Problems in which there are more unknowns than equations are called indeterminate. We have all had experience with wobbling restaurant table, which we usually level by putting folded paper under one of the legs. If a big enough elephant sat on such a table, however, you may be sure that if the table did not collapse, it would deform, just like the ties of a cup. Its legs would all touch the floor. The forces acting upward on the table legs would all assume definitely and different values as in the figures, and the table would no longer wobble. But how do we find the value of these forces acting on the legs? They cannot be found from the laws of static equilibrium alone. To solve such indeterminate equilibrium problems, we must supplement equilibrium equations with some knowledge of elasticity, the branch of physics and engineering that describes how real bodies deform when forces are applied to them. Elasticity. When a large numbers of atoms come together to form a metallic solid, such as an iron nail, they settle into equilibrium positions in a three-dimensional lattice, a repetitive arrangement in which each atom has a well-defined equilibrium distance from its nearest neighbors. The atoms are held together by interatomic forces that are represented by spring in the figure. The lattice is remarkably rigid, which is another way of saying that the interatomic springs are extremely stiff. Many ordinary objects such as metal ladders, tables, and spoons are perfectly rigid. Of course, some ordinary objects such as garden hoses or rubber gloves do not strike us as rigid at all. All real rigid bodies are to some extent elastic, which means that we can change their dimensions slightly by pulling, pushing, twisting, or pressing them. Three ways that a solid might change its dimensions when force is acting on it. Tensile stress, shearing stress, hydraulic stress. What the three deformation types have in common is that a stress or deforming force per unit area produces a strain or unit deform. What the three deformation types have in common is that a strain or deformation forces per unit area produces a strain or unit deformation. Stress is tension or compression is force divided by area. Strain is relative length change or relative volume change. The stresses and the strains take different forms in three cases of the figures, but over the range of engineering usefulness, stress and strain are proportional to each other. The constant of the proportionality is called modulus of elasticity. So that is, stress equals modulus multiplied by strain. Stress equals modulus multiplied by strain. What tension and compression, either pulling out or press in, it will have a delta L. Delta L can be more positive or negative. For simple tension or compression, the stress is defined as F over A, the force divided by the area over which it acts. The force is perpendicular to the area, as you can see in the figure 8. The strain or unit deformation is then the dimensionless quantity delta L over L, relative length change. The fractional or sometimes percentage change in the length of the spaceman. FOA, this is equal to E multiplied by dl over L. Strain causes strain. This is modular. The modulus for the tensile and compressive stresses is called Young's modulus and is represented in engineering practice by the symbol E. Because the strain is dimensionless, this is no dimension. The modulus has the same dimension as the stress, namely force per unit area.
We'll show how the stretch of a spring varies with the applied force, using this hanging spring and a set of weights. With no weights added, the bottom of the spring is here. Here is the spring extension with 10 newtons of added weight. $20 newtons. $30 newtons. Now we'll add the same set of masses to a different spring, leaving the markings from the first spring on the screen for comparison. 10 newtons. $20 newtons. $30 newtons.
All materials will stretch when pulled hard enough, even the steel wire. We'll hang increasing amounts of weight on the wire to show how the amount of stretch varies with applied force. This mirror is balanced on a small platform attached to the bottom of the wire. If the wire is stretched, the mirror tips and deflects a laser beam, as shown in this animation. The deflection of the laser beam is therefore an indicator of the amount the wire stretches. $20 newtons. $40 newtons. $60 newtons. The amount the wire stretches is directly proportional to the applied force.
Examples. A steel rod of 1 meter long and 1 centimeter in diameter, hence one subcompact cup. It always hooks low here. The stress is more than SY here. Okay. This is S yearly. Okay. And the relative length change is about 0.5%. If you hang two cars, you call it permanent stretched. If it goes that, you never come back. It's permanent stretched. Okay. So if you put 3 cars, then it'll break. The stress larger than ultimate. Okay, US ultimate. This here is corrupted. Okay, this is a relative change. Okay, this is the stress. Although the Young's modulus for an object may be almost the same for tension and compression, the object's ultimate stress may well be different for the two types of stress.
All materials will permanently deform or break if they are stretched too far. But the amount they can stretch and still spring back varies tremendously from one material to another. We'll demonstrate that with these two springs, one made of brass and the other copper. The brass spring is stretched out to a distance almost 3 times its original length, and it springs back unchanged. Here's what happens when we stretch the copper spring. Even a small amount of stretch is too much for the copper. It springs back a little, but won't return to its original length.
Stress equals modulus times strength. 2. Shearing. Shearing at force on the surface, not perpendicular, on the surface. So it will have a delta x moment. Okay, we call it F over A equal to G delta L. This is delta L over L. Okay, it's called a shearing modulus, G. Okay, shearing stresses play a critical role in the buckling of the shafts that rotate on the rod and in the bone fractures caused by bending.
This torsion lathe will be used to demonstrate how the amount of twist in a rod is related to the applied torque. A thin copper rod is held between 2 supports. This end is stationary, while this end is free to rotate and twist the rod. Hanging weights on a metal band wrapped around this disc supplies the torque. The amount the rod twists can be read on this angle scale. Here is the amount the rod twists when 250 grams is hung from the band. Here is the amount of twist with 500 grams hung from the band. We'll now repeat the demonstration using a thicker copper rod. For comparison, we'll leave the last set of markings on the screen as we take new readings. $250 grams. 500 grams. 1,000 grams.
3. Hydraulic stress. We know that stress equals modulus times strain. Okay, and in our case, this is like you put in the liquid in the water, something like that one. The pressure, the stress is pressure. Okay, this is a modular called a Buck modular. This is a relative volume change. Yeah. So the stress is P. P is F over A. The strain is relative change of volume. A B is Buck modulus. In general, solid where their rigid atomic lattice are less compressible than liquids, in which the atom or molecules are less tightly coupled to their neighbors.